Hello. In the last video, we talked about critical points of functions of more than one variable and how to find them. And in this video, we're going to talk about how to use that to classify critical points. So let's just review the situation in the case when you have a function of one independent variable. So review in the case of a function f of x. So let's say you have a function f of x, and let's say that c is a critical point. So suppose that c is a critical point or critical number of f of x. Then the point c comma f of c might have, it might be a local maximum or local minimum point. So some possibilities of what happens when x is c is you could have, so let's say that f of c is, this y value. Okay, so this is f of c. It's the point c comma f of c. Okay, it might be the case. So what's happening is, let's say that f prime of c is equal to 0. Remember that we might have the situation where f prime of c is undefined and c is in the domain of the function f. But let's just look at the case when f prime of c is 0. That means that the tangent line at the point c comma f of c is horizontal, right? So when you zoom in, the graph looks like a straight line, basically. That's what it means. So some possibilities are you could have something like this. That's one possibility. And when you have something like this, then f has a local maximum at c, at this critical point. Now, it's not necessarily an absolute maximum, because it could be that your function kind of just keeps going up forever, like in this direction, right? And then these y values here are actually bigger than these y values. To say that you have a local maximum means that in the immediate vicinity of c, so that means that if you look a little bit to the left and a little bit to the right of c, okay, if you just only look at the y values corresponding to these values of x, and you look at the corresponding y values, the y value at c is the biggest. Okay. So what this means is in the immediate vicinity, that means slightly to the left and slightly to the right, vicinity of c, the value f of c is the largest value of f. That's basically what it means when you say that f is a local maximum. So that's one possible outcome. That's one possible scenario. And another scenario is that you could have, say, okay, so c here, and then f of c is, say, here. So you have this point. You could also have a local minimum. You could have something where it's like this. So in the immediate vicinity, this y value at x equals c is the smallest. And again, this might not be an absolute minimum, because there could be situations where the function gets below f of c. Right. So in this case, f has a local minimum at C. Meaning that in the immediate vicinity, so slightly to the left and to the right, f of C is the smallest. That means the smallest, meaning that it's like less than or equal to any other value, is the smallest value of f in the immediate vicinity. So slightly to the left and slightly to the right is what I mean. Okay. Now those aren't the only two options. Another possibility is, there's one more possibility, which is that you have neither a local max nor a local minimum. So you could have something like this, or you could have something like this. This has a, at these points you do have a horizontal tangent line, but in these examples, f has neither a local max or a local min at C. And one way to tell, so the question is, if you have a critical point, C, does your function have a local max, a local min, or neither? Like which scenario do you have? And one way to tell is something called the second derivative test. So we're still reviewing the Calc 1 situation. And what happens is you look at f prime of C, the second derivative. So you calculate the second derivative and then plug in C. If this guy, this number, if that's positive, then what happens is that your derivatives are increasing. So the scenario is you're going to have something like this, because the first derivative is 0 at x equals c, and then slightly to the left it has to be negative, and then slightly to the right it has to be positive, because that's what has to happen in order for the derivative to be increasing as x goes to the right. So you have something like this, and then that's f has a local minimum at c. And if the second derivative is positive, if the second derivative is negative, then f has a local maximum at c. So you have a situation where the graph is going to go like this, because again, at x equals c, the derivative is 0. If the second derivative is negative, that means that the first derivative is decreasing. So your slopes have to be decreasing as x goes to the right, and what that means is that to the left of x equals c, immediately the derivative has to be positive, and then it has to decrease to 0, and it has to become negative. And that's what's going to cause you to have a local maximum at x equals c. And if the second derivative is 0, then you can't conclude anything. So this test is inconclusive. The test is inconclusive. It's not saying that the function has neither a local max nor a local min. It's actually, if the second derivative is 0, it could be either of these scenarios. It could be any of these scenarios. So the good example to remember is if you have f of x equals x to the 4th power, that's going to look like this. So you have a local minimum at x equals 0, but if you take the second derivative, so this has a critical point at x equals 0, but if you take the second derivative, you get 12x squared, and then the second derivative is 0, but you still have a local minimum. And if you did f of x equals negative x to the fourth, you would have a local maximum. So you really don't know which situation you have, and then when you have something like that, where the second derivative test doesn't tell you anything, where the second derivative is 0, you have to use a different method like the first derivative test. Okay. So that's the second derivative test. A quick review of that. Now let's talk about what happens. So we're done with the review. Now let's talk about what happens in the case of a function of two independent variables. Well, you can still have a local maximum or local minimum. So let's say that, suppose, now instead of C, I have A comma B, right? I have this one point. So let's say that this is a point, and this is a critical point of my function f of xy. Then there are a few possibilities, just like in the case of a function of one variable. You could have, so you could have a local maximum at the point A comma B. And what does that mean? That means that in the immediate vicinity of A comma B, the value, okay, let's say that this is Z. Z equals f of xy. The value of Z at A comma B is bigger than all the values of Z in the immediate vicinity. So you could have something like, okay, I don't know how to draw this, but you could have something like maybe this is your point A comma B, and your function, okay, it's gonna look something like this, except this is a function of like, this is a function of two variables, so it's, I don't know, maybe it's like that. Right, so at A comma B, you're at, the value of Z is this, and it's a local maximum. Like if you look at the immediate vicinity, so if you just look at all the xy's here, when you plug those values, these values of xy, into your function, the one at A comma B is the biggest value of the function. So local maximum, that's what it means. So in the immediate vicinity, so when you just kind of look all around the point A comma B, why do I keep doing this? In the immediate vicinity of AB, the largest value of Z, or the largest value of F, is at A comma B. Okay. So that's one possible scenario. A second possible scenario is that F has a local maximum. Oh wait, that's what we said. The second possibility is that F has a local minimum at A comma B. And to get a picture of that, just imagine flipping the picture that I just drew upside down. So you have something like, So here's a comma b, and okay, let's see if I can draw this upside down. Okay, you have something like, oh, I don't think I can draw this upside down. Okay. Yeah, this is too difficult. Yeah. Okay, you could have something like this. I don't know. Wow. Okay. Something like that. Right, like this is the graph of the function, and when you plug in a comma b into your function, you get this value, which is the smallest value of z, again in the immediate vicinity. By the way, I'm purposefully drawing these pictures so that the value of z at a comma b is not the smallest when you look at the entire xy plane, right? If you look at the entire xy plane, then this value here, this value of z is smaller than this value of z. But in the immediate vicinity, like if you just zoom in enough, this point really is the lowest point in the graph. So, in other words, in the immediate vicinity of a comma b, f, the smallest value, the least value of the function is at a comma b. If you plug in a point that's close to a comma b, but it's not exactly a comma b, then the value of z will be larger than the value at a comma b. Okay, so that's a local minimum. However, there's one more possibility, which is that you can have something called a saddle point. So this is option 3. Well, I'm going to say option 4. Option 4 is that's neither 1, 2, or 3. But you could have a saddle point. F has a saddle point. And what that means is that in the immediate vicinity, remember when we're talking about the derivative and the gradient, you have to imagine that you're zooming in at the point a comma b with like a microscope, right? You're not looking at the whole graph of the function. You're taking the point a comma b and then taking a microscope and zooming in and just looking at what happens in the immediate vicinity of a comma b. So of a comma b, there are points x, y where f of x and y, f of x comma y is less than or equal to f of a comma b, and there are points where f of x comma y is greater than or equal to f of a comma b. Actually, can you have neither a local max or I feel like I mean, doesn't that eliminate all the possibilities? Yeah, I think you must have either a, oh yes. Yeah, your critical point, sorry. Your critical point is either a local max, local min, or a saddle. Okay. Right, because if you think about what the definition is saying, it just rules out all the possibilities. So here, f is neither a local max nor a local min, basically. What it means is that you have a saddle point, so not local max nor min, but it is a critical point. And what's going on is that you have a scenario where if you have your point a comma b and you zoom in, then maybe there's a way to draw these things. it's like, it looks like a Pringle chip. Basically, like you have something like this, but then you have something like this, and then your function looks like this. Wow. Something like that, right? It's this kind of oddly shaped thing. Okay, I was just trying to draw a smaller one. So you have something like this, where so you have a point here above this point AB, and if you look at the immediate vicinity of AB, you see if you look at the points, say here, maybe the points above it are like this, and then you have z values that are bigger than f of AB. But if you look at the x and y's that are along here, you might get like the z values might look like this, and then those z values are smaller than the value of the function at a comma b. So your function's neither a local max nor a local min, but this is a critical point. The tangent plane is going to be z equals f of AB, right? In all these situations, the equation of the tangent plane is z equals f of AB. Okay. Should I just draw that in the other ones too? Right? These are the tangent planes. The tangent planes are horizontal. Okay. So now the question is, how do you classify the critical points? And the analog of the second derivative test in single variable calculus is called the second derivative test. So this is the multivariable calculus version. And I'm just going to say what it is and not explain in this video why it's true. And in another video, I'll give an explanation of why it's true. But to understand why it's true, you need to know about linear algebra, and you need to know actually more linear algebra than is usually taught in a first semester linear algebra class. You have to know about something called positive definite matrices. And I have a video on positive definite matrices, and if you watch that, you'll get a better idea of why the second derivative test is true. But there's very little intuition behind why the theorem is true when I state it in the form that I'm going to state it in. Okay, so there are some technical situations, technical conditions. You need second partial derivatives to be continuous, and okay, but that's going to be the case in all the examples. So we're just going to skip that, and then you have a critical point a comma b, and what you do is you look at the matrix of second partial derivatives like this. So you have this matrix of the second partial derivatives, and oh, they don't give a name for this matrix. Okay, so you look at this matrix, and then you take the determinant of this. So, okay, this is called the Hessian matrix. Right? you have these numbers. You take the second partial derivatives and then you plug in your critical point AB, and when you plug in your critical point AB, you're going to get these numbers. So this is a 2 by 2 matrix, it has 4 numbers, and you take the determinant of this. So let's say that D of AB is the determinant of this 2 by 2 matrix. Now if you don't know what the determinant of the 2 by 2 matrix is, what it is you take this number on the top right, sorry, top left, that's Fxx AB times the number on the bottom right, Fyy AB, and then you subtract the product of the diagonal terms here. Now the theorem that we're using is that f sub xy is the same as f sub yx. So really you can just do f sub xy and then take that and square it. Okay, so you have this. That's this number D of AB. Okay, so the scenario is there's a bunch of possibilities. Okay, if let's say that the determinant is negative. Then A comma B is a saddle point. Okay, so if the determinant is, negative 5, then A comma B is a saddle point. What happens if the derivative is positive? If the derivative is positive, not the derivative, sorry, if the determinant is positive, then you have two possibilities. If the number on the top left, that's f sub xx at AB, if that's positive, then f has a local min. Then the critical point is a local minimum. And if, this is the subcase. If the number on the top left, f sub xx at AB is negative, and the determinant is positive, then A comma B is a local maximum. And the last possibility is if the determinant is 0, if D of AB is 0, then the test is inconclusive. Meaning that you don't know what the critical point is. So that's the second derivative test. It's not obvious why this is true. So in a future video, I'll give some indication of why it's true. But let's just do an example. Let's say that you had the function f of xy equals x squared plus y squared plus x squared y. And the question is, find and classify the critical points of the function. So we need to take the partial derivatives, set them equal to 0. So f sub x is going to be what? 2x plus 2y. No, 2x plus 2xy. Right? You set that equal to 0. F sub y is going to be 2y plus x squared is equal to 0. Now from the second equation, I can solve for y in terms of x. So I get 2y plus x squared is 0. That means that 2y is negative x squared, so y is negative x squared over 2. And then I can plug that into the first equation and get 2x plus 2x times negative x squared over 2 is equal to 0. And what will that give me? 2x, let's see, the 2's will cancel, and then minus x cubed is equal to 0. Now I can factor out an x. X times 2 minus x squared is equal to 0. Remember, you don't want to divide both sides by x. If you took the 2x minus x cubed equals 0 and divided both sides by x and got 2 minus x squared equals 0, you would end up missing the critical point where x is 0, right? When you divide by something involving a variable, you have to be super careful not to divide by 0. So that's why it's better to factor the x out instead of dividing both sides by x. So now you have x is equal to 0, 2 minus x squared is equal to 0. Well, if 2 minus x squared is equal to 0, then you're going to get x squared is 2, and so x is going to be plus or minus root 2. So you're going to have 3 values of x, 0, root 2, and negative root 2. And now you need to plug those back in, but since we found that y is equal to negative x squared over 2, right, if x is 0, then that's going to tell me, so y is, let me just write down y is equal to x squared over 2 again. So if x is equal to 0, then I get y is 0. If x is root 2, that gives me y is equal to 2 over 2 is 1. And then if x equals negative root 2, I get y equals also 2 over 2, right? So I get 1. Did I do that right? Oh, it's negative x squared over 2. Okay, negative 1. So my critical points are 0, 0, root 2, negative 1, and negative root 2, negative 1. So that's the first part of the problem, to find the critical points. Now we need to classify the critical points, and for that we need the second partial derivatives. So we found the first partial derivatives. Now let's find the second partial derivatives. Okay, I'll do that here. So f sub xx is equal to 2 plus 2y, right? F sub xy is equal to 2x, okay? F sub yy is equal to 2. So my matrix, my Hessian matrix is going to be plus 2y, 2x, 2x, and 2. And now I just need to plug my critical points, my 3 critical points in here. So for 0, 0, I get the matrix 2, 0, 0, 2. Now what do I do when I calculate D, my determinant? That's 2 times 2 minus 0 times 0 is going to be 4. That's positive. And this is the one where I have subcases, right? I need to look at f sub xx, this number here. My f sub xx is 2 at 0, 0, and that's positive. So when you have a positive determinant and your top left number is positive, then you have a local, do you remember? It's a local minimum. So 0, 0 is a local minimum. Okay, we classified that one. And now we have 2 more, root 2, negative 1. When I plug those in, I get 0 here, 2 root 2 here, 2 root 2 here, and 2 here. Now when I calculate d, I get 0 times 2 minus 2 root 2 squared, and that's going to be a negative number. I get negative 8. The exact number isn't important. The point is that it's negative. And since d is negative, that tells me that I have a what? Maximum, right? A local maximum. Oh wait, no, I don't. I have a saddle point. Sorry, I have a saddle point. And one more, negative root 2, negative 1. Okay, so let's figure out what I get when I plug them into, when I plug these values in. I get 0 here, negative 2 root 2 here, negative 2 root 2 here, and 2 here. And again, I'm going to get d is equal to 0 times 2 minus negative 2 root 2 squared, and that's going to be negative 8, which is negative. And so this is a saddle point. And that's the answer. We found the critical points and we used the second derivative test to classify them. So let's just review what we did in this video. This video, we reviewed the second derivative test for classifying critical points in single variable calculus. And then we talked about the version of the second derivative test when you have a function of two independent variables. We mentioned that the critical points come in three varieties. It could be a local maximum, local minimum, or a saddle point. And we explained how to tell which kind of point you have. You look at the matrix of second partial derivatives, and then there's this kind of checklist criterion for which one you have. So you could have a saddle, local minimum, local maximum, or the test might be inconclusive and you can't tell which one you have. And then we did an example. And in the next video, we'll talk about why this theorem is true and get some more intuition behind it. But it's not necessary to know why it's true, especially if you haven't taken a lot of linear algebra, because without linear algebra, it's very hard to explain why this is true. I mean, there's no real intuition for why this is. It's not like you look at it and say, oh, of course, of course this is true. It's not obvious that this is true at all. Okay. But in the next video, which I guess will be optional if you're not required to take linear algebra, we'll explain more about the science behind this second derivative test. Okay, thanks.